multiplied, and the numerators get like a cross multiplied and added, right? So maybe let's make this 2 to illustrate this point. So I have like a no. X minus 2 and then a plus 2 times x plus 1, right? That's how you add fractions, right? Denominators just multiply together and the numerators you cross multiply, or you make them over the same denominator. You don't have to worry about LCMs or nothing. You just put the denominators together, cross multiply and add, and you got the thing. But now if we look at this, this is 2x plus x, so that's 3x. And then 2 minus 2. Is that right? X, okay, so, and then we can also expand this. So that's x squared minus 2x plus x, so that's minus x, and minus 2. So if we were given this expression to integrate, so if your problem just gave you this expression to integrate, it might not be clear just exactly how to do that, because it's a fractional function. It's a polynomial over a polynomial. So basically what partial fractions does is it says any kind of fractional function like this, some polynomial divided by another polynomial, you can break into its constituent parts and then integrate. So this reverse process of going, if you were given this, going back here is called partial fraction. Right? And the idea is you can always sort of do this. You can basically always do this with rational functions. If you have a polynomial or a polynomial, if you have something like a square root in there, or like a sine or e to the x, then of course we're not saying you can do that. But if you have a polynomial, something x squared, x cubed, whatever, and the same thing in the denominator, you can always break it down. So what's necessary for this kind of decomposition? So do you understand what's happening here? You have something that's easy to, it might be presented in a form that's difficult to integrate just because it's been added together. And you want to break it into its parts. Those are just logs after that, or maybe a couple of arctans. You'll see. So what do I mean by that? See, if I had something like 1 over x squared minus 1, yeah? Or let's take 4 over x squared minus 1. This is sort of the expression that I'm looking at on the right side. Let me maybe put it on the right side. So we have 4 over x squared minus 1. I can go back. To go back, first thing I need to do is see what that denominator is a product of, right? First thing to do is factor the denominator. Now how do you factor x squared minus 1? X plus 1 minus 1. Okay, so that means there is an x minus 1 and an x plus 1 here. That's just what the denominator is. Then you say, well, if there is this linear factor and this linear factor, x plus 1 and x minus 1, that means this this function over here must be something over x minus 1 and something over x plus 1, right? And it turns out if the degree here is less than the degree here, if this is quadratic and that's linear or constant, then you can always choose this so that there are constants a and b that make this happen. You can always choose constant to make it happen. Break it. Then the question is, how do you figure out that constant? We just multiply by this original function, original denominator. Every multiply the whole equation left to right by that denominator. Yeah. Yep. Glad you're paying attention to what I'm saying. So you get we break this denominator, and the way to figure out what these constants a and b must be, can someone tell me what they must be here? Minus 2 and 2, that's right. And yeah, that's the way to do it. Maybe I'll show you a simpler. So basically, if you multiply by this expression, x minus 1, x plus 1 everywhere, what do we get? Let's take this and multiply by the denominator. Clear the denominators, right? So I'll get a times x minus 1, x plus 1, but a was over x minus 1. And then there is b times, I'm multiplying everything by this denominator, x minus 1, x plus 1, and b was over x plus 1. And on the right, we just have 4, right? So this is a polynomial equation because everything in here, all the denominators clear out, so to speak. So it's a polynomial expression. In this expression now, if you plug in x equals minus 1, x equals 1, for example, this becomes 0. The only thing that doesn't become 0 is the guy that was over minus 1. Does that make sense? So if I plug x equals minus 1 into this expression, not this expression, but this one, the only constant that survives is the guy who was sitting over x minus 1. Go? So for example, at x equals 1, we get a times 1 plus 1 plus b times 0 is 4. That means a is 2. And then at x equals minus 1, I get a times minus 1 plus b times 1 minus 1 plus 1, that's 0. Oh, sorry, something is wrong. Oh, plus 1 here, minus 1 here. Minus 1 is 4. So this one is 0 now. That means b is minus 2. And it's true, you can then check, once you get this, you can just then check, is it true? Can I really write 2 over x minus 1 plus minus 2 over x plus 1? And does it really add to 4 over x squared minus 1? And it does. Because the 2x and the minus 2x cancel, the 2 and the plus 2 makes 4. So that's the general procedure. I'll show you how to do this in detail, but once you write it like this, once you break it down like this, all you have to do is one by one plug these solutions into that to get the constants one by one. There's no solving involved, almost. Okay? Now, when can this not work is, for example, if I had instead 4 over x squared plus 1. Okay? So why doesn't this work? We can do it with a 10, but what I mean is, can I break it into something of x minus something and then x, x plus something and x plus something else? Why not? This is x squared plus 1. Also, one way to see is that the discriminant of this thing is negative. Remember, quadratic things have discriminants, right? B squared minus 4ac. That number here is 0 squared minus 4. So that's minus 4. So it's negative. That means its roots are not real. Right? So you can't break down this quadratic. So now you may be worried. Wait a minute, does that mean there are expressions where you just can't factor? Right? But luckily, this is the worst that can happen. You can always factor any algebraic expression over the real numbers, into linear and quadratic factors. Okay? Any algebraic expression can always be factored into linear and quadratic factors. That's a fact. And basically, we have the technology to prove it. Like, we've already done this stuff in calculus to see why that's true. But I don't know if we need to establish why that's true. It's got to do with the fact that if you have a cubic, for example, or higher, say you have a cubic, then it must have a root. Why? Because a cubic is either coming from infinity, one infinity, and going to another infinity. It must cross the x-axis somewhere, maybe 3 times, but maybe just once, but it must cross once. So that means that x minus that crossing point is one factor, and so on. Okay, so that's the general of what, the whatness of what it is. That you break down fractions of polynomial over polynomial. Rational functions you break down into simpler pieces. Those are easier to integrate. Now, how do you do it in practice? So, basically, so what did I just say? So, any polynomial, so here we're thinking of the denominator, can be broken down, factored into linear and quadratic factors. So you can always write, so if you have something like something over x cubed plus x, we can write it as that's something over x times x squared plus 1, and that's the best we can do, a linear and a quadratic. This quadratic you can further factor. But if you get a quadratic, something like something like this, that you can factor. Right? Something like this you can factor. Even the one with the minus 1 you can factor. It's just the roots are more involved, like something plus, something root, something, right? Even in that case, you can factor it. It would just be worse to write it down. Let's maybe write it, or no. So this one, you could definitely, even though it's quadratic, you don't just leave it there, you go down to its linear factors, right? So here it would be what? Like this? Alright. So then you know that this one, for example, you could factor as some number over x and some other thing over x squared plus 1. It turns out in this case, if you are on a quadratic, you have to have a linear. It's not just a constant over a quadratic, it may be a general linear function over a quadratic. Okay, so any questions about this? Yeah, there's 3 terms in on the right. An A, a B, a C, a D, whatever, however many terms you have. So that's the general strategy. So, first of all, right, so, yeah, maybe I should make this clear. If I have, this is slightly more complicated than what I'm about to say, but basically, if you have something like x minus a, or x plus a, x plus b, x plus c, and then maybe a x squared plus d, right? Something like this. You could always break it. So the claim is that expression like this can be broken down into something over x plus a, some constant over x plus a, plus some constant over x plus b, plus some constant, some number basically, right, over x plus c, and then some other, not a number but a linear expression over the x squared plus d, if d is positive, for example. Then you can't break it down any further. So you leave a linear thing on top and you're done. And then to integrate such a thing, obviously the linear part, the dx over this part is u substitution. Whereas the e over this part, that's arctan. Is something squared plus 1, something squared plus d here. The integral of that is with arctan. Right? Is this too loud, by the way? Today I feel like it's too loud. Right? So you can easily make a mistake and go down like a huge rabbit hole. So I took some time yesterday to come up with a nice function that factors nicely, divides nicely, and all that has integer roots. Only 2 people are sleeping. Great. Okay, let me copy this exactly. Okay, maybe let me use this word. Right, you get the idea here. What can happen? Say I have an expression like x to the 4 minus 3x squared plus 9x minus 4 is divided by x cubed plus x squared minus 2x. Right? Suppose I'm tasked with integrating this. Doesn't look very nice. Yeah, so the denominator can be. Yeah, so the first thing to do here is note that this is what's called an improper fraction, which is to say what? The numerator is a higher degree polynomial than the denominator. So you're an improper fraction if your numerator is the same degree as the denominator or higher. So if they were both cubic, it would still be improper. If this was quadratic and this is cubic, that's proper. Okay, a fraction is proper if the numerator is smaller, strictly, in degree than the denominator. This is like with numbers, right? Like something like 7 over 3 is improper. So what do you do to it? You write it as 6 over 3 plus 1 over 3, and then you say, oh, the 6 over 3 is a 2, and then I have a 1/3. That's really the fractional part, otherwise it was 2. Right? So that's the same sort of thing we want to do here. We want to say the numerator is higher degree, so we break it down into lower degree. So we're going to have to do long division. Are you ready for this? Have you done this before? You have done this. Don't tell me you've never seen it in high school. Long division? Come on, you guys are just like messing with me now. You're just saying, oh, we've never seen anything in high school. You know, it's the thing when you divide one polynomial with another. Yeah, so you can do it in all sorts of ways. For example, putting it in a box works. And so we want to divide that polynomial by that polynomial. This is like back to elementary school, right? Divide the number by another number. See how many times this is going to that one, right? But this is real math. I'm telling you, none of that integral whatever. This is at the core of it. So how does one do this? Yeah, you look at the biggest thing here, the biggest power here, you look at the biggest power in what you're dividing with, and you say how many times does this biggest power go into that one? Right? What do I multiply this with to get this? Not what do I multiply this with, just this guy. What do I multiply x cubed with so that I get an x to the fourth in this case? And the answer is x. So I should multiply by x, but I can't just multiply this guy by x, I have to multiply this whole expression by x. So what happens? X cubed times x becomes x to the fourth, x squared times x becomes x cubed, and then 2x times x becomes minus 2x squared. Right? Now this whole thing needs to be subtracted from above, because we're saying that part of it we've taken care of in the quotient. So you subtract the rest of it, which means you turn all the signs around in this one. So this becomes a minus, this becomes a minus, and this becomes a plus. So it's x to the 4 minus x to the 4, minus 3x squared plus 2x squared. So that's a minus x squared. First I have this x cubed thing, hold on. So there is a minus x cubed, minus x squared. So there is this minus x cubed. There is also minus 3x squared plus 2x squared. So that's minus x squared plus a 9x minus a 4. So we're still here, right? Now what do I do? Now it's minus 1. X cubed goes minus 1 times into minus x cubed. So to make this look like this, I need to multiply by minus 1. So that minus 1 has to be added to the top, to the quotient, right? Please tell me you are following this, right? We're in college. So what do we get? Minus x cubed minus x squared plus 2x. And now we need to flip the signs. So this becomes a plus, this becomes a plus, this becomes a minus. The minus becomes a plus, the minus becomes a plus, plus becomes a minus. This goes, and so does this. And we're left with 7x minus 4. Now what do I multiply x cubed by to get 7x? Nothing. So this is the remainder, right? And this guy here is the quotient. We're not saying you can. Okay. So that means this expression is what?
X minus 1 plus the remainder of the...
Yeah, it's the quotient separately with no denominator. And the remainder is still over that denominator that it was over before. So the same denominator is now over the remainder. So we have 7x minus 4 over this x cubed plus 2x minus, what is it? X cubed plus x squared minus 2x. Right? These partial fraction questions, even though every step is very easy, they can be long. So give yourself a lot of time on the exam to do these, because every step is just obvious. So we're dividing, now we're multiplying, now we're dividing, now we're adding. But it adds up. So this is the guy that I'm eventually going to integrate. Right? So first step, you break it down like this. Now this bit is just, how do you integrate this? This is x squared over 2 minus x. Now this is the part that needs work. Okay, so what do you do here? You try to factor the denominator as much as you can into linear bits and quadratic bits. quadratic irreducible ones. So quadratic ones that have negative discriminant. Okay? Quadratic expressions so that b squared minus 4ac is negative. So it looks like this one is all linear, right? Is it? So we have x minus 1 plus 7x minus 4, and the denominator here, you can factor out the x. Is it again this? Minus 2. So, by the way, can you guys factor on your calculator? You don't need to worry about this. What? Ask someone. But on your calculator, apparently nowadays on calculators you can just factor polynomials, which is great. But you should also know that the coordinator of the course knows this. The one who writes the exam, he knows this fact, that you can use calculators to factor polynomials. So, you know, he might give you something that the calculator can't. You are allowed to use a calculator on the exam, yeah. Factorization? No. We're past that stage now. Now it's just... Okay, so we got these linear factors, right? Yes? With me? Okay, so let's see. So we have x minus 1 over here, and this guy, what does partial fractions say about it? Yeah.
I don't think that's correct.
Oh, really?
Because the expression on the left board,
Oh,
x squared minus x minus 2, that gives x plus 1. Oh wait, that's, no, yeah.
that one was the one with the plus 1 minus 2,
Yeah.
and this is the plus 2 minus 1.
Okay, yeah.
So we know we have some number over x, some number over x plus 2, and then some number over x minus 1, right? Typically these numbers a, b, c come out to be rational numbers, like 5 over 13 or some crazy number like that. I've chosen them in this example so that they come out nice. But don't be fooled, they come out as rational numbers generally. So we're saying this expression 7x minus 4 over this whole thing can be written as just basically every one of the things in the denominator gets their own denominator, and it splits the whole thing up open, right? And then these guys are very easy to integrate. So the question is, what are a, b, c given that we want 7x minus 4 on top, right? So this is where you do this business I was talking about. Let's do this over here for a second. So let's say I have 7x minus 4 over this x plus 2, x minus 1, is it? And I know that it's some a over x, some b over x plus 2, and some other number over x minus 1. Let's call this numerator of x over denominator of x. Okay, just for a second. This numerator of x over denominator of x. And let's just multiply everywhere by the denominator. Right, so I'm saying basically the numerator of x, which is 7x minus 4, is a times the denominator over x plus b times the denominator over x plus 2 plus c times the denominator over x minus 1. Right? Just multiply everywhere by this denominator. That clears the denominator here. That just leaves the numerator on the left. And over here, everyone gets multiplied by the denominator. Now, why am I doing this? If I plug in x equals 1 into this expression, over here I can't, because I'll get 1 over c over 0. But here now I am allowed to take x equals to 1. or more precisely, I'm allowed to take the limit of this expression as x equals 1. So I can first cancel x, because this has x minus 1 in it. So that x minus 1 does cancel in this expression, but not in this and not in this. So if I put what I get is the numerator at minus 1, which is 7 times minus 1 minus 4, is this a part is 0, this b part is 0, and I just get the c part, right? Does that make sense? So I get c times whatever is left of the denominator after you divide by x minus 1. So c times minus 1 times minus 1 plus 2. So you can immediately say, that's 1 times minus 1, so the minus c is minus 11. So c is 11? That can't be right. Oh, really? You're right. So you're getting this out of this? Oh, you should plug in 1, you're right. Yes. Thank you. So for this one, we should plug in 1, x equals 1. That's what makes it 0 here and here. So 7 minus 4 is 3, that's 3 times 3 then, no? Okay, let me just do this properly. Okay, so let me write this with all its bells and whistles. So we have a times this denominator over x. So that's x plus 2, x minus 1. Right? There's an x here and then you divide by x. And then there's a b, x plus 2 gets cancelled, so there's x times x minus 1. There's a c times x minus 1 gets cancelled here, so x times x plus 2. Oh. No, it should be minus 3 though, in my notes. Unless I made a mistake yesterday. So we'll see. So now what I'm saying is, you look at this, right? And there's multiple ways of doing this. You could expand this out, multiply the whole thing out. You get some quadratic on the right, and you have a linear thing on the right. Then you say some expression of a plus b plus c is 7, some expression is 4, some expression. You get a system of equations in a, b, and c. There's a system of 3 equations in 3 variables. It gets out of hand very quickly. On the other hand, what you could do is you could just, you know, this is true for all x. This expression has to be true for all x, because this equals that for all x. It's not we're saying at this x it is true and that at some other x it's not. That means we could just plug in x equals whatever. So for example, at x equals 1, this would be 0 and this would be 0 because it has an x minus 1 in it. Only the guy who was sitting over x minus 1 won't be 0. So to get c, you plug x equals 1. Okay, it's just this one process. So at 1 we get c times 1 times 3 plus 0 should be 7 minus 4, that's 3, right? So c is 1. And then can someone from the back tell me what I should plug in x as? So I plugged in x equals 1 to get c. What I should plug in to get b?
Minus 2.
From the back, I said. Good, yeah, so that's right. So minus 2, you plug in minus 2. And why is that good for b? Because only the guy b was over x plus 2, so he would have had denominator 0, but we cleared denominators. That means this will be 0 and this will be 0. The only thing not 0 will be b. So we'll get b times minus 2, minus 2, minus 1, that is 7 times minus 2. I don't like this. Okay, so what is b then? X minus 1, x plus 2, right? Oh.
Minus 3.
Anyway, so yeah, so this is 16. Oh, I'm sorry, 18 over 6. Minus 18 over plus 6. Yeah, minus 3. B is the guy who's minus 3. Okay, okay. And then what do we do for A? X has to be 0. Because this has x, both of these will become 0, and we get 8 times 2, 2 times minus 1 is minus 4, so that A is 2. Right? So, moral of the story is that once you found these three numbers, you can plug them in to the expression. So we have A, which is 2. We have B, which is minus 3. So I'll just write minus 3 over x plus 2. And we have C, which is 1. Right? So this expression, the numerator had higher degree. So what do? You first divide, long divide, until you get the numerator to give smaller degree, and long division is done until you get a remainder of some smaller degree. So you always can do this. You come to this point, now you factor the denominator as much as you can. You can always go down to linear or quadratics. Then each linear term just gets its own denominator with a constant, and each quadratic term gets a linear term on top. Then you figure out those constants in any which way you like. I think your calculators may even tell you what the constants are. Do your calculators do partial fractions? They have to. This is like such an immediate, such an automatic process. They might. But if they do, again, you have to remember that the person writing the exam knows this. So he will only give you problems that your calculator can't do. Or his last year, yeah.
I have a doubt.
Yeah.
So, what would we do if the degree is same of the numerator and denominator?
You divide. So same is still improper.
But then, what if there's also constant? Like, so, suppose the numerator is x cubed instead of x raised.
Yes. So you divide, you get just a constant as the quotient, and the remainder will be quadratic or less. It won't be cubic.
Oh, so we do long division again.
We have to start with long division, yes. You always bring it to a point where the numerator has less degree. Then, and only then, can you conclude that every linear thing gets a constant rather than another linear thing on top, right? And then you go from there. But this partial fraction business only works if your numerator has strictly less degree than the denominator. So is that clear for everyone? You know, last semester I was teaching linear algebra, and I didn't know this until the final, but people can just plug in 3x3 matrices into their phones and get characteristic polynomials, eigenvalues, things like this. You guys don't know this, right? Anyway, but yeah, it's on the calculator. So all the questions on the exam were 4x4. Nothing up to 3x3, because calculators can do 3x3. So the professor writing the exam is like, no. Everything is 4 by 4, which makes it harder for even us, because to grade you have to go through like a whole mess of people messing up in different ingenious ways. Okay, so that's the basic story of partial fractions. Now let's get into the not so basic theory of it. Yeah. So how can this process get complicated? It looks very simple, right? You break it down, you integrate, whatever. So the integral part, you do it in your head. Right? If I had to integrate this, that's the same as integrating this. That's the same as integrating this. And this is easy to integrate. That's the whole point. So it's not easy to integrate. And basically, this solves the problem of integrating any fraction, any rational function, meaning any polynomial over polynomial. Anything that looks like that, you can integrate by partial fractions. And it'll always turn out to be a bunch of these log and arctan terms. Okay, now how can this get complicated? So what we had, that example over there, is the first case of 4 cases. There's 4 cases. One where there is distinct linear factors. Okay. The denominator can be factored into linear terms, and all of those linear terms are different. That's the first case. Now what happens, so this is distinct linear factors. So meaning the denominator can be factored x minus alpha 1, x minus alpha 2, up to alpha n, where basically the alpha I are distinct. They're different from each other. Right? Does that make sense? The second case is repeated linear factors. And so here what happens is some of the roots are the same. You have some linear factors, but some of them are the same. For example, I could have some expression over x minus 1, or let's do x minus 5 cubed times x squared plus minus 1. Right? It may be that the factors you get are x minus 5, then another x minus 5, then another x minus 5, and then an x squared minus 1. In this case, the proper way to decompose this as a partial fraction is to have a constant over x minus 5, and then, does anyone know? No, but that's 3 things of x minus 5, so if you add them, it'll just be a plus b plus c over x minus. That's just a constant over x minus 5. You can never get the cube. Yeah. So you go up to that power, 1 by 1. So the next constant should be over x minus 5 squared. The next constant should be over x minus 5 cubed. So because it was a cubed factor, it gets 3 pieces. One with just x minus 5. The other one with x minus 5 squared, and the third one with x minus 5 cubed. If you think about it, and there is a plus this term, right? Something over x minus 1 plus something over x plus 1. So that would be the complete decomposition of this expression. But if you think about it, what we are doing here with these is we are saying this is x minus 5 cubed, and then on top is a times x minus 5 squared plus b times x minus 5 plus c. In other words, we are taking a general quadratic over this cubic, which is what it should be. All we know is that it's 1 degree less. Yes? No. Yes, but there would be, it would be power 6, but there would be a cubic x minus 5 above that cancels with everything. Yeah, here you should really think about the LCM rather than what I was saying before. You just multiply. Okay. All right. So this case is obvious, right? The first distinct linear factor, you just break it. A over this plus B over this plus C over, and so on. This one, if there is a repeated thing, you repeat it in the factors as well, but each one gets a constant if you go up in the powers. So for example, if I had the expression 1 over x to the 5 x minus 2 squared, how would I write it as a partial fraction? Yep. And then? And just x minus 2 with another constant EFG over x minus 2 squared. So that would be the expansion. Okay? And I won't try to find ABCD here, but you can. It'll take you ages. Maybe not. I don't know. I'm not going to do it. Okay? They can get very involved very soon. Then the third case is quadratic irreducible factors, meaning what? Yeah, something like x squared plus 1, x squared plus 5, x squared plus x plus 1. Something quadratic that cannot be factored over the real numbers. Yeah? So, if I have some expression like third case is distinct quadratic irreducible factors. So what do I mean by quadratic irreducible? It's any expression of the form ax squared plus bx plus c where b squared minus 4ac is less than 0. So when you write that whole thing minus b plus or minus square root of b squared minus 4ac over 2a, the roots of the quadratic, the thing under the square root is a negative number. So if the thing under the square root is a negative number, it doesn't have real roots. And to be able to split it as a, factor it, you would have to put its real roots there, but you don't have them. So you can put its complex roots there, but we're not dealing with those kinds of things in this class. Then your integral would have answer 1 over I, arcsine I, and then you know what to deal with. So these are irreducible quadratic factors. So for example, if I have something like 1 over x squared plus x plus 1 times x squared plus 2, something like this. And maybe there is a linear factor. Right? So they're distinct quadratic irreducible factors. This guy, b squared minus 4 times 1, that's minus 3, that's negative. So you can't factor this. This one also, b squared minus 4ac is minus 8, so you can't factor it. This one is linear. So what happens here? Each of the quadratic ones gets a what?
Linear.
Gets a linear factor on top. So the x squared plus x plus 1 gets some ax plus b. You don't know what some ax plus b, right? And then the other guy, x squared plus 2, the other factor, gets some other linear thing. Can you tell me? Yes? Say that again. B, I already have b. Cx plus d. And then what do we have? E over e over x plus 5. And that's it. So we break them down like this. And so since these are quadratic irreducible factors, there is no real number I can put in here to make this 0. Right? That's what it means to be quadratic irreducible. That there is no real number that you can plug in for x and make this expression 0. So it's not like that trick where you just plug in something and make it 0. You really have to figure out what these constants are. Maybe I should show you an example of how to do it in real life. Do I have an example cooked up? Let's do a simple one. Just so we see how, because A, B, C, D, E, that's a 5 by 5 system of equations, and I don't want to solve that. It'll take like 2 classes worth. So let's do a simple, and the simplest can be like a 3 by 3. So let's do that. And I won't show you something that has like a polynomial long division involved. Right? You guys already know that business. So let's see how, for example, if it was x minus 2, x squared plus 1, something like this. Right? Suppose I'm trying to integrate this. First thing I should do is break this down into partial fractions. And they would be some a over x minus 2 plus some bx plus c over x squared plus 1. So this is what we can always break it down. Now, we know on the left hand side this is 1 over x minus 2 x squared plus 1. So that 1 is what will help us figure out the a, b and c, right? So what do? You just multiply by the denominator throughout. Multiply everything by the denominator. That means 1 by itself is a times the other guy, because a is over x minus 2. So a times the other guy plus bx plus c times x minus 2. And notice, this is not an equation you solve for x. We're saying this is true for every x. X equals 1, 2, 3, minus 1, minus 5, 10. This is true for all x. So this is something that will help you figure out what a, b, and c are, not what x is. It's not something you solve for x. It's true for all x. So this is for every x. Okay, if this is true for every x, that means we have an ax squared plus bx squared, right? Plus a bx plus a cx plus a plus a minus 2c, is that right? Can someone please check this?
What did we do here?
Just expanded this.
Minus 2b.
Thank you. And what else is wrong? So this one is a bx squared minus 2bx plus cx minus 2c, and this one is a ax squared plus a, and then I was trying to do 2 steps at once and put all the square things, linear things, and the constant things. So So basically we have a plus b x squared plus c minus 2bx plus a minus 2c is 1, right? This needs to be true for all x. The only way this is true for all x is if this polynomial is the same as the polynomial 1. And here you should be thinking of this polynomial 1 as it's not a quadratic, right? But you should think of it as 0x squared plus 0x plus 1. You should think x squared has coefficient 0, x has coefficient 0, and then there is 1. And that tells you if this polynomial is to be the same as that polynomial, then a plus b must be 0. And c minus 2b must be 0. And a minus 2c must be 1. It doesn't have, so the thing that's not 0 is important. Everything is important, but you should take care not to say everything is 0. So we get the system that a plus b is 0, c minus 2b is 0, and a minus 2c is 0. And then you can play games with the system. You can say, for example, we gotta do something here. So maybe we just subtract these two, right? Subtract these two, and we get, what do we get? B plus 2c. That thing minus this. So b plus, sorry, this is 1. I just did what I told you not to do. So this is why, because it's easy to do this. So you subtract this one from that one. So that minus, so plus 2c is going to be minus 1 then. Now I have two equations involving b and c. So maybe I'll double this equation and add these two. So add these two. This was subtracted these two. Let's add these two. So we get what? C plus 4c, that's 5c, is minus 2. So c is minus 2/5. So this is a minus 2/5. And then the rest of it just falls out of it, because if c is minus 2/5, then b, which is c is minus 2/5 minus 2b is 0. So that's 2b. So b is what? Minus 1/5? Yes? So let's just put a minus here. Or actually, the way we could write this may be nicer is just put a minus 1/5. Just the x plus 2 here. And then a is the minus of that. So it's plus 1/5. Right? So that's how you figure out these constants. And this is like in real life. They come out rational. They don't come out like nice, like 5 or 10. What? How long do we have? 7 minutes? Okay, let me just say, finish this thing so that you can go home and say we are experts in integration. Is when you have repeated quadratic. And what do you think happens here? You guys know what happens here. So something like x squared plus 1 to the 3 times x times x. No, it's the same sort of thing. A quadratic irreducible gets a linear term, right? But he is being cubed. So first he gets a linear term, then his square gets a linear term, then his cube gets a linear term. Just like with the linear factors. So here we would have some ax plus b over x squared plus 1, then some cx plus d over x squared plus 1 squared, and then some ex plus f over x squared plus 1 cubed, and then a efg over x. Right? So it's just the way you would do it in the repeated roots. Here it's repeated quadratic bits, so each one gets his own. You go up to the power of the quadratic. I really need to make this sheet with everyone's name so you could just sign it.